couple of reactions we looked at on Tuesday as a review. This first one, we have the hydration of an alkyne. Hydration of an alkyne with water and acid is going to give us the most stable carbocation. So in this case, that's going to give us the double bond or the carbonyl on the secondary position. Okay, so we end up with ketone. The last one is the same, but in this one, which we really haven't faced too many times, right, is that we do have two possible products, right? So this is not a symmetric alkyne. So therefore, when we do the hydration, we get two secondary sp2 carbocations, right? Both of those are the same stability. So therefore, we'll have two possible products. Okay. If it was symmetric, which is what we usually show, right, we'd only have one product. Okay. Okay, so there was a couple of other reactions that I forgot about, and that's one of the reasons that we ended class. So I knew there were a couple of reactions I had forgot about. One was ozonolysis. Right, so ozonolysis, here we have we use ozone and then some type of reducing agent. So DMS is one, that's dimethyl sulfide. We could also use zinc and acid. This cleaves that double bond, and then whatever's attached is left, right? So we end up with the carbonyl. I'm going to put an H there because that's what was there at the beginning. We don't show it normally. Okay, so in this case, when we have ozonolysis, we can end up with a ketone and an aldehyde. And then if we had an example, right, if we had something like this with ozonolysis, the way to think about that is I'm just going to cleave that double bond, right? So I'm going to break that double bond. I'm going to add oxygens to both sides. So in this case, that'll be an oxygen. I'm counting to make sure I get it right. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So we'll end up with this compound, right? You could end up with two aldehydes. You could end up with two ketones, right? It depends on what's attached to that alkene, right? So an alkene will just be cleaved. Another one is the Friedel-Crafts. So, you know, we had just seen this. So Friedel-Crafts acylation. So we didn't really point it out when we were doing these reactions, but we're making ketones, okay? And in this case, right, they're always ketones. We wouldn't make an aldehyde. And both of these are review, right? These are old reactions. So you've got the hydrations of the alkynes. You've got the oxidations of alcohols, ozonolysis, and Friedel-Crafts acylation. All of those are old reaction synthesis. Questions about these? Okay, so that brings us to reactions of aldehydes and ketones. You know, and the first thing we need to think about on the aldehydes and ketones is that, you know, we can draw these electrons going up to give us a resonance structure. right? Where the oxygen would have a negative and the carbon would have a positive. So when we think about our carbonyl, right, we can think about it as a partial positive and a partial negative. We also, the pi bond acts as a leaving group, right? So that pi bond can break. So if we add electrons to that partial positive, that pi bond gives us an obvious leaving group and a good leaving group, right? Since we're not even actually breaking a sigma-sigma bond, we're breaking a pi bond. So therefore, the way that aldehydes and ketones are going to react as acceptors to nucleophiles. So they're going to be electrophiles, right? So nucleophilic aromatic, nucleophilic addition is one of the main reactions we're going to be looking at. Now, generically, right, and this is going to be one of those places, especially with aldehydes, but even more so when we get to carboxylic derivatives, is that thinking about these not as distinct reactions, but thinking about them as modifications. So if we think about this reaction as a nucleophile, right, coming in and reacting with that electrophile, and then if we have some proton source, right, we can end up with this. What we're going to be looking at is different types of nucleophiles and how they react. But the reaction, the mechanism is about the same. So when you see an aldehyde and a ketone, right, and we're looking at those reactions in this chapter, the question is there a nucleophile there? If there's a nucleophile there, that nucleophile is going to react with a carbonyl. Now we can have base catalyzed, which this is it, base catalyzed. Right, where the nucleophile, and I should put a negative charge on it. The nucleophile is negative, right? And the nucleophile is coming in as a negative to give us this reaction. We can also have acid catalyzed. And in that case, what happens is we have a potential nucleophile that is attached to an acid. And the first thing here is a proton transfer. That proton transfer now activates this, right? Now we have this positive, making this even more electrophilic. And then the nucleophile can attack the carbonyl carbon to result in about the same product, right? So in the first case, we have an active nucleophile. It is strong enough to do the reaction. In other cases, we activate the carbonyl by protonating it, okay? So you can kind of think about this like our SN1 and SN2. Sometimes for SN2, the nucleophile was a strong nucleophile and we had a good leaving group, so therefore it reacted. Sometimes we had a weak nucleophile, so we needed to activate the leaving group. That's what we're doing here, right? Strong nucleophiles, base promoted, we're going to end up with the nucleophile attacking first. In the case where we have acid, we're protonating the carbonyl then becomes the most reactive part, okay? Now, when we look at aldehydes, what's the difference between an aldehyde and a ketone? The aldehyde reacts faster. Than ketones. Okay, and there's a couple of reasons for that. One is sterics. If we look at this group with the hydrogen, and now I'm going to draw out my hydrogens here. So both of these you can see they're not that sterically different. But if we have two methyl groups, right, and those are freely rotating in normal temperature ranges, right, that the aldehyde, right, on this side is less sterically hindered. Okay, so therefore it's going to be faster because of sterics. Okay? The ketone is always going to be more sterically hindered than the aldehyde, because the aldehyde is always going to have one side, right, the hydrogen side, that's going to have no sterics or limited sterics. The hydrogen is in the plane here, so therefore you can think about it, it's got two flat sides it could react with, where on the ketone, we're always going to have kind of this revolving alkyl group there with two hydrogens. So we're going to have to get around that to get to that carbonyl. The other is electronic. So if we think about the oxygen, the aldehyde versus the ketone, okay, and it's a little bit hard to think about them this way. So let's go ahead and show them as the resonance contributor. So what we have here is the oxygen negative, right, with the positive hydrogen here, CH3. Over here, we have the oxygen negative hydrogen here. And if we look at this one, we can get hyperconjugation from one side, right? So the carbon can donate electron density through the sp3 bond back to the positive. But in the ketone side, we could do that on two sides, right? So if we think about stability of a carbocation, what this is primary carbocation versus a secondary carbocation. So therefore, this one is going to be more electrophilic. Because it only has one carbon with hydrogens on it that could stabilize that, versus a ketone that will always have two. So when we do these reactions, aldehydes react faster than ketones, and there's a few examples where that's going to be important. Questions about the reactivity between aldehydes and ketones? So we're going to be looking at different classes of nucleophiles. We're going to start with one that you've seen before, Grignard nucleophiles. And if you remember, we had Grignard reactions, right? We would add in, let's say, this methyl Grignard. And that made a bond, a hydrogen bond, right? A carbon bond between the epoxide. So we saw this in ring opening epoxides. The other place that Grignards are very useful is in carbon-carbon bond forming with carbonyls like aldehydes and ketones. So if I added CH3, CH2 Grignard, right? So that's MgBr. That's a nucleophile. Right, that's going to add two carbons to the group. So looking at the mechanism, this comes in and attacks there. Right, you can think about the magnesium being there. It's a counter ion, it's not essential. But since we have the mechanism, we can show it floating around there. Right, so that's the first step, just nucleophilic attack. And then second step is proton transfer. So then we pick up a proton to get us to the stable alcohol. Okay. The importance of this Grignard reaction is you're making a carbon-carbon bond, right? So that means you're changing the carbon skeleton. And those are always reactions you should put a star on, right? So go up here and put a little star, right? This is going to be anytime you see a carbon skeleton change, you need one of these reactions, right? And Grignard's did that with the epoxides. You can also do it with the carbonyls. It also works with ketones. Right, and we can get the alcohol. Okay, questions about this one? Right, so whatever the Grignard is, how many carbons you attach. Yeah. Not really. Secondary Grignards don't react as well in most cases, but they will react. You know, tertiary carbonyls, Grignards don't react very well. But primaries, you could have a big long chain, right? And these have been used to take two large groups and actually hook them together. So there are examples of pretty massive Grignard reactions between two parts of a molecule. Okay. And it's used in biological synthesis. This Grignards don't occur biologically. There's a biological similar reaction. But to make pharmaceuticals, you can see Grignards being made because there's often carbonyls and alcohols in pharmaceutical species. Okay. All right, so this is a good example of a nucleophilic addition, right? So this is a nucleophilic addition with a carbon nucleophile. Okay, we can also have reactions with acid catalyzed, right? An example of that would be making an acid chloride, right? So if we look at this, we can end up with the geminal hydroxychloride. Again, this is an acid catalyzed, so the first step in the mechanism here is to react, oops, switched it to bromine. First thing that does is we activate the carbonyl. And then once we've acted that carbonyl, then the nucleophile can come in and attack the electrophilic carbon at the carbonyl. So questions about this one? So this halohydrin is not as useful as the 1,2 halohydrins, right? Because 1,2 halohydrins I can turn into epoxides, but every once in a while you'll see these halohydrins in systems. All right, now what we're going to do is we're going to go through a set of different types of nucleophiles based on the element. So we saw a carbon one, we saw the acid. Now we're going to go into the group of oxygen nucleophiles. Then we'll do nitrogen, then we'll do sulfur, and then we'll get to hydrogen. If you just put a ketone or aldehyde in water, it will become a hydrate. Now, the percentage of that depends on whether it's a ketone or a aldehyde. So if we look at acetone, acetone is about 90% ketone and only about 1% of the hydrate. But if we look at acetaldehyde, which then we see that it forms about the opposite, right? About 99% of the hydrate form. And in the old days, this is changing pretty quickly, but in the old days, they would use formaldehyde, right, to preserve things. And they still use formaldehyde in some preparation of the deceased. And what happens is you put in formaldehyde, sans water, right, without any water. And then what happens is it starts to use up all the water. And without the water, right, the body won't decay. And so the old way of prepping samples in a biology lab was to use a lot of formaldehyde. Now, formaldehyde is not that healthy, right? So they've moved away from formaldehyde. And in fact, in most counties, you have to, if you are embalmed, you have to be buried in a sealed, waterproof coffin. Sometimes they'll sell that to you as an advantage, but depending on the county, you might have to be in that, because with the formaldehyde, that's actually, that's toxic, right? So it has to, you have to protect the environment. So we don't use that much, but what happens, this is what happens. You put the formaldehyde in here, it absorbs all the water as the hydrate, right? And then there's no more water. If there's no more water, no bacteria, no breakdown of the body. And so it can last longer, okay? Or usually it's what you see in biology labs, right? Specimens, okay? Now what they use is a mixture of alcohols, right? So you might still smell a little bit of formaldehyde in older samples, but now what they use is alcohols. The alcohols work a little differently. An alcohol doesn't take the water out of the specimen and therefore deny the water. It also turns out that this hydrate is toxic, but what the alcohol does is just, it's toxic, right? Ethanol is toxic. It will kill bacteria. Isopropanol will kill bacteria. So what they do is they put a mixture of alcohols in there, and that mixture of alcohols keep the bacteria from breaking down the material, right? It doesn't last as long, but that's what they do now. And it turns out, you know, alcohol, ethanol, and I forgot what the other alcohol is. They usually have that mixture. It's not as toxic to humans. If you drink enough ethanol, you will kill yourself, right? But it's not as toxic as the formaldehyde. And if you didn't know that ethanol was toxic, you should know that ethanol is toxic. So, you know, consume wisely if you're going to consume. Okay. Right. So how does this work? So what happens is the water, right, is going to react with this carbonyl, and we're going to do this mechanism several times, so get used to this, right? The nucleophile is going to attack the carbonyl. My pi bond is my my bond breaking, right? I'm going to get the negative water here. Okay, we then get a proton transfer because this is positive. And you'll see some books try to do the transfer directly up, but I prefer this method. It also will work better in the next step. All right, so we get this, that gives us this water here, and then I've got the protonated form here, and then I get another proton transfer. And I'll I'm just moving these around. If that bothers you, we'll leave it where it was. Right, and I get the hydrate. So we get nucleophilic attack. A proton transfer, right? And then a proton transfer. Okay. The book uses this language, and I find that this is a good time for you to bring it back up from chapter, I think it was 6, right? Because we're going to see some pretty long mechanisms. And these mechanisms are really going to be mixtures of nucleophilic attack, proton transfers, and loss of leaving groups. And if you know how many proton transfers, it's helpful. So if you kind of learn them as nucleophile, proton transfer, proton transfer, proton transfer, loss of leaving group, proton transfer, sometimes you can understand how long that mechanism is and not shorten it. Okay, yes. Which I didn't draw it. I stopped drawing the hydrogen. So yeah, still a aldehyde. Okay. Okay. But as we said before, right, we can do this as acid or base promoted. So let's look at acid promoted. So if we just put alcohol or ketone in water, we're going to end up with some percentage of hydrate. But if you really want this reaction to go, then what you do is you either use base, right? Right, and this can, and you can drive it one way or the other with the acid or the base. So if we look at the base mechanism, so this is base catalyzed. So again, going back to your generic, and you're going to see these over and over again. So sometimes it's helpful if you just make a note to yourself that this is a base catalyzed. So here with the hydroxide, the first thing that happens is the hydroxide reacts with the carbonyl. So we get nucleophilic attack. And then in the second step, we get the proton transfer. And then we have the hydroxide. Right? So it's just base catalyzed. We're not using up the base, we're just base catalyzed. We can also do acid catalyzed. And the acid catalyzed, instead of using the base, we'll just use acid and water. And again, same idea on the mechanism. If we got it in acid, the first thing that's going to happen is we're going to protonate our carbonyl. Okay. So the lone pair on the carbonyl are going to pick up the proton, so we get a proton transfer. Now we have an activated carbonyl, right? So then the water can come in. And then to get to the stable hydrate, right, we need to remove the proton. So we'll get a proton transfer. Questions about this one? Okay, so these are all hydrates, right? And the hydrates have this equilibrium process. We can make this reaction go faster by adding that base or the acid. And again, anytime you see an aldehyde or ketone in a water mixture, this could be part of the mixture, right? That'll be important when you look at some of your biomedical and biochemistry reactions. You'll see this step happening quite a bit. And this is the basic mechanism for that. After hydrate, we can form acetals. The acetal is going to be a little bit different, right? Where instead of adding water, we're going to add alcohols. Now, because of the sterics, usually this doesn't happen very rapidly without adding some kind of catalyst. So, you know, acid catalyst. And if I let this go to completion, right, I'm going to end up with let's turn this into an aldehyde. So that's an aldehyde. So this is an acetal. And just to make it more confusing for you, they call this a ketal. So aldehyde becomes acetal, ketones become ketals. You'll see them mostly just referred to as acetals, but there is a slight distinct difference. Now for the acid catalyst, again, it's a catalyst. Sometimes you'll see in the book, they'll just put H plus. Sometimes you'll see them put the H plus inside of brackets. If they see the H side in brackets, that just means acid catalyst. The ones that you're going to see them use most often are going to be sulfuric acid. Oh, I don't know why I made a weird S. Sulfuric acid, right? But in some cases, you're going to want to not have any water around, and sulfuric acid always has water. It's an aqueous acid. So for anhydrous conditions, you'll see PTSOH, right? Or you might see it written TSOH, right? Both of these are interchangeable in most textbooks. And what that is para-toluene sulfonic acid. So there's the toluene, right? And then the sulfonate acid. This one is organic soluble. So therefore you can use the para-toluene sulfonic acid in organic solution. So you can reduce the amount of water, okay? So if you want to use an acid catalyst without adding water, the TSOH or the PTSOH is a good example. Okay. The mechanism on this one, and we'll use the ketones since I keep forgetting the aldehyde hydrogen. Since we're using an acid catalyst, the first step is the protonation, right? So we're going to activate this. Once we have that activated, now we can have the alcohol attack the carbonyl. So we get a proton transfer followed by nucleophilic attack. Turn the corner here. Right, so now we end up with this species, right? We're going to do a proton transfer. So here we did a proton transfer. We did a nucleophilic attack, right? Proton transfer. And then this species is an important one to note. This is a hemiacetal. And we'll see how these are important in a little bit. In most cases, it's hard to stop at a hemiacetal, but there are some very important examples of hemiacetals and why they stop at the hemiacetal. But usually we don't stop there, right? We still have the same conditions. And so what happens next is we get a proton transfer. So we get a proton transfer. It's a long mechanism. And then at this point, right, I've got water as my leaving group, and I've got a lone pair on my oxygen at the bottom. So this can come back, kick this off. And now what I'm doing is inverting it. Right, to get this intermediate. And then this intermediate can go through a nucleophilic attack with another methanol. And if we put in our groups, right, this is going to be a proton transfer. Right, this is a loss of leaving group. We're losing the water. Here we get nucleophilic attack. Right, and then a proton transfer. Questions about this mechanism? The other thing to note about this mechanism is that all of these steps are reversible. So could I reprotonate could I take the ketal here and reprotonate it to make this species? Yes, if I had acid in solution, I could do that. Could I have this lone pair here, kick this group off as a leaving group? Yes. So this is reversible. Could I then have, you know, this group get attacked to go me by water to get me back to here? So could water come and attack that group? Yes, that could happen. All right, so that's reversible. Could I redo the proton transfer? Yes, that's reversible. Could I redo this? Yes, that's reversible. Could I redo this one? Yes, that one's reversible. And even the first protonation is reversible, right? So this whole reaction is reversible, right? What depends on whether it's going to go forward to the ketal or back to the ketone? It's going to be whether I have an excess of the alcohol or I have an excess of water. okay? So if we think about what I'm losing here, right, what I've lost in this whole process is I've lost water, right? So if I remove water from the solution, I can drive this forward, or if I just inundate it with a bunch of an alcohol, right? So you'll see most of these that we're making, we're going to be using methanol, ethanol, propanol, things where it's easy to get lots of alcohols. That's not always necessary, but if it's not the case where you can use a lot of alcohol, you have to do the opposite and remove water to get this going forward. Okay, so this is a reversible process. Okay, questions about acetal and ketal formation? Okay, this leads us to protecting groups. And if you remember, if I can take functionality A, right? So if we think about this reaction, and I wanted to do a Grignard on here. To get this, right? That wouldn't work because this will react with that. So what I have to do is take and turn the alcohol into the tosylate. Right, so I protect that alcohol, that proton as a tosylate. Then I do my reaction. And again, you should have seen this in organic 1. All right, so if I added to my methyl group, I still have the tosylate. And then what I want to do is remove that protecting group. So protecting groups are a way of doing a reaction at one site when the other site might have been a problem. So I protect. And what protect really means is I'm changing the functional group, right? I've gone from an alcohol to a tosylate. So functional groups change, functional group's not going to react. Then I do a reaction, right? And then I deprotect. And again, this is an example for organic 1 to remind you of the concept of protect, react, deprotect. For ketones, we can do a similar thing because now we have this hemiacetal, we have this acetal ketal formation. So I can take a ketone or an aldehyde, I can react it with an alcohol. In this case, we use a dialcohol, again with a trace acid. That then will form a acetal or a ketal. But then if I just add water, right, and the acid catalyst, I can remove that group. So our sequence is protect and deprotect. This cyclic acetal is the one you're going to see most often, but you could have done it with 2 methanols or 2 ethanols, right? The cyclic one makes a nice stable intermediate that is allows you to do other reactions easily and then comes off relatively quickly, but you could have also done it with the methanol. So an example of how we would use this, let me switch colors. If I wanted to go from this ester and ketone to this to the alcohol and the ketone. So if I want to do that reduction, I'd have a problem. If I use sodium borohydride, and remember sodium borohydride, that should be 4. Sodium borohydride we can do in methanol. But if we use sodium borohydride with this, sodium borohydride will reduce ketones to alcohols, but it won't reduce carbonyls. And again, this is a little bit of review. So we wouldn't get what we wanted, right? We want to reduce the ester in the presence of the carbonyl. If we use lithium aluminum hydride, so now lithium aluminum hydride, we always have to use the water separate. Now what we end up with is that is strong enough to reduce both. So we can't just use one of our hydride reducing agents to get this product. So what we do is we take this with the ester, and now the hemiacetals and acetals react with carbonyls. So I take and I add and form the ketone, right? So we could use PTSOH. We don't want to use an aqueous acid, so we won't hydrolyze the ester. Now we've done that step. Now we can add lithium aluminum hydride. Okay, could get the anion, right? But then in the last step, we're going to add acid and water, and the acid and water will remove the protecting group and protonate the alkoxide. Now, if I wanted an aldehyde and a ketone, right? So questions about this one? So again, the steps, we're protecting, right? We're reacting, and we're deprotecting. Questions about this? Another example would be if we had an aldehyde and a ketone. If we did a protecting group here, and we need to be careful, right? One equivalent. Which one is going to get the protecting group first? The aldehyde or the ketone? The aldehyde. So using this, we could protect aldehydes in the presence of ketones. Right? One equivalent, yeah, one EQ. If we put an excess, we would protect both of them, right? We would get that ketal on both of them. So hemiacetals, like I said, usually if we have an excess, we go all the way to the product, but there are a few examples of stable hemiacetals. So if we take a carbonyl, with one methanol, we end up with the hemiacetal. Right, and then in the second one, we end up with the acetal. And this one is usually unstable. But there are specific examples where it would be stable. One of those is cyclics. So if I have a ketone with an alcohol on it, in this case, or an aldehyde with an aldehyde on it, and I put it in an acid solution, what I can end up with is a stable hemiacetal. And if we color code our oxygens, it might help. This oxygen here is that oxygen. And then this oxygen here is that oxygen, right? So that's coming back around and reacting with itself. So we can think about it this way. Let's go ahead and show the mechanism. Right, since we're in acid, we'll go ahead and protonate first. So we'll get a proton transfer. It's going to pick up that proton. Give us this species with the positive here. We got the oxygen. Lone pair, right? Then this is going to react here. And that forms, oops. That forms our ring. That's not what I want to draw. And then we'll get a proton transfer. Okay. Questions about this one? Now, why this is important, okay, is that it is related to carbohydrates. So a carbohydrate is a sugar, right? So if we look at a carbohydrate, this is glucose. Right? And as glucose, right, this is an energy molecule, carbohydrates, we're gonna, but what if we want to store that, right? So you use the carbohydrates. If we want it to store, it turns out the way these react is they start at the aldehyde, right? So if I wanted to store this, let's say as a starch, how would I store it? Well, I need to not have the aldehyde there. And that's where we get the cyclization, right? And so we end up with this. And so you'll see carbohydrate shown in this form. In this form, I can't oxidize that carbonyl, that aldehyde, because now it's a hemiacetal. And starches, right, and other storage compounds for carbohydrates are these cyclic ring systems. So a starch is just a bunch of these all put together, right? And then what happens is you unzip those as your body needs that, right? So you eat a potato, it starts to metabolize it, you get the sugar from the potato, right? The potato is mostly starch. And then what happens is that you end up with the aldehyde gets turned into energy, right? And so that's what's happening in these molecules. So with sugars, right, our carbohydrates, they're stabilized and stored as hemiacetals. Okay, questions about these? Okay, I was going to start nitrogen nucleophiles, but it's getting late. Let's try some practice on these. So let's do a little try this, and then we'll start on nitrogen nucleophiles on Tuesday. So first thing, let's make some aldehydes. Let's take a couple of minutes to do this one. Okay, let's go ahead and take a look. So on ozonolysis, right, once you recognize that that's ozone, you can just break that double bond, right? Put in oxygen on both sides, leave everything else the same. Again, it's not shown, but there were hydrogens there. So then make sure you count, right? So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Carbonyl going down with hydrogen, right? And since this was a di-substituted, one on each side, we end up with the dialdehyde. So ozonolysis aldehydes and ketones depends on your original alkene. Okay, questions about this one? The second one, we're just getting a Friedel-Crafts acylation, but we do have a directing group on there. Methyl is not very sterically hindered, right? So with the methyl group, primaries and secondaries, primaries are usually not very sterically hindering. So in this case, we can get both the ortho and the para as our product. And then the last one, PCC, is a anhydrous oxidant. So a primary alcohol will go to an aldehyde. If we had used something like sodium dichromate and acid, right? This is in sulfuric acid, right? This is an aqueous condition. I would have ended up with the carboxylic acid. So the PCC stops at the aldehyde. Questions about any of these? Again, these are review. So every time we see one, we're gonna review them. We're just using it a different way. Okay, let's look at the reactions we did today. Let's take a little while to look at these. Feel free to look at your notes and talk to your neighbors. Okay, let's take a look. Okay, in the first one, all right, the Grignard is going to react at the carbonyl. So therefore, we're going to have the addition of the right number of carbons, right? So 1, 2, 3, 4, 1, 2, 3, 4. And then in the second step, we get the protonation. So first step, we attack the carbonyl. So this is a Grignard attack on a carbonyl, makes a carbon-carbon bond. The biggest mistake on these is what? Adding the wrong number of carbons. So just count. It's always good to count. Right, in the second one, we have ethanol with an acid catalyst. So in this case, we're going to end up with the ethanol acetal. So you add the 2 alcohols on there. And then the last step, right? We have a ketal, right? And then that ketal with acid and water is going to reverse and go back to the ketone. So this is a deprotection step. Questions about either of these? Okay, let's try one more. Oh. Not use the same one over and over again. I'll redraw that because I took up way too much space. But I'm not changing it. Okay, let's take a minute or so. Okay, since we're running short of time, we'll go ahead and look at this one. Could we do this with PCC? No, that only end up with an aldehyde, right? Could we do it with chromic sodium dichromate or chromic acid and acid? No, that would oxidize both groups, right? Because an aldehyde can oxidize to a carboxylic acid. So what we're going to have to do is protect this side, right? We're going to have to hide that aldehyde. Then we can oxidize. Right? And then we can deprotect. So to protect, we use the cyclic diol, right? Or the diol here with acid. Then we can use the sodium dichromate. Right, to do the oxidation of the primary alcohol all the way up to carboxylic acid. And then in the last step here, we add an excess of water in acid. Okay. And then we'll get our product. Okay. So this is a protect, react, protect sequence. Okay. All right, that's enough for today. On Tuesday, we'll look at nitrogen nucleophiles and sulfur nucleophiles. I'll post some problems out of the chapter so you can get started on those. They should be due. I should get them up